Chapter 20, problem number 1. How many calories of heat are required to raise the temperature of 4 kilograms of water from 50 degrees Fahrenheit to the boiling point? All right, let's take a look at number 1. It says how many calories of heat are required to raise the temperature of 4 kilograms. So we have a mass of 4 kilograms. And we're going to go from 50 degrees Fahrenheit to the boiling point. So our T initial is 50 degrees Fahrenheit. But you know our specific heat that we're going to use is in degrees Celsius or degrees Kelvin. So we need to change this 50 degrees Fahrenheit to either the Celsius scale or the Kelvin scale. So we recognize that the temperature in Celsius is 5/9 times the temperature in Fahrenheit minus 32. From the previous chapter, we have 5/9 times 50 minus 32, 5/9 times 18, which would be 5 times 2 or 10 degrees Celsius. So that'll be our initial temperature actually. And we're told that the final temperature is the boiling point. So our final temperature is 100 degrees Celsius. So our change in temperature is going to be the final minus the initial. 100 minus 10 or 9 degrees Celsius. Now I can kind of get away with using the Celsius scale in this one because if I'm looking at changes in temperature, that's the same no matter whether I use the Celsius scale or the Kelvin scale. But if I'm just looking at temperature, pure temperature, then I would have to go one step further and change these to kelvins. So keep that in mind. So we want to go through a temperature change of 9 degrees Celsius. The heat that we need to add is our mass times specific heat times the change in temperature. And if we have 4 kilograms, we have 4,000 grams. Our specific heat for water is 1 calorie per gram per degree Celsius. And we have 90 degrees. So this gives us 3.6 times 10 to the 5 calories. So it'll take 360,000 calories to raise 1 kilogram of water from 50 degrees Fahrenheit to boiling. Number 2, a 5-gallon container of water, approximately 20 kilograms, having a temperature of 212 degrees Fahrenheit, is added to a 50-gallon tub, approximately 200 kilograms, of water, having a temperature of 50 degrees Fahrenheit. What's the final equilibrium temperature in degrees Celsius of the mixture? Well, let's take a look at this. We're going to add something that's hot to something that's cold, and they're going to come up with the equilibrium temperature. And one way to look at this is that the heat that is lost from the hot object is going to be equal in magnitude to the heat that is gained by the cold object, or in other words, the hot water combined with the cold water. And so I can write that mass 1 times the specific heat times the change in temperature of the hot water should be equal to mass 1 times the specific heat, mass 2 times the specific heat 2 times the change in temperature of the cold water, at least the magnitude of that change in temperature. Heat loss should equal the heat gained. So, one way to write this, we have 20 kilograms here The specific heats will cancel out on both sides because we're dealing with water on both sides. And we have the final temperature minus the initial temperature absolute value. So we'll take the hottest one first. And we'll say we're going from 212 down to some final temperature, which in Celsius would be 100 degrees Celsius minus some final temperature. Over here, we have 200 grams, and we're going to go up from original temperature of 50 degrees Fahrenheit, which in the last problem we determined was 10 degrees Celsius. And our final temperature will be T, so this difference will be T minus 10. And so let's just solve this for T. So I divide both sides by 20, and so I have 100 minus T equals 10 times T minus 10, or 10T minus 100. So I have 200 is equal to 10T minus T, which is 9T. T is equal to 200 divided by 9. That's all right. I'm sorry, this should be a plus. This should be 11T. So 200 divided by 11, which is 18 degrees. Number 3, a 5 kilogram piece of lead with a specific heat of 0.03 calories per gram per degree Celsius, having a temperature of 80 degrees Celsius, is added to a 500 grams of water having a temperature of 20 degrees Celsius. What is the final equilibrium temperature in degrees Celsius of the system? All right, we're going to approach this in a similar way as the last problem, only this time we have lead as our hot object and water is the other object. So we'll say again that the heat lost by the lead should equal the heat gain at least in magnitude by the water. And so I can write this as the mass of the lead times the mass, the specific heat of lead, times the change in temperature of the lead. I'm using an L subscript instead of a PB. Should equal the heat gain, which would be the mass of the water times the specific heat of water times the change in temperature of the water, at least in magnitude. So I'll write this, we had 5 kilograms piece of lead, so our mass will be 5,000 grams. I'm using grams because our specific heat is in terms of grams. And we're told that the specific heat of lead is 0.03 calories per gram per degree Celsius. So I have 0.03 there. My change in temperature will be the final temperature. Well, it will be the hotter temperature, 80, for the lead minus the final temperature. And that should equal the mass of the water, which was given as 500 grams, times the specific heat of water, which is 1. And here we'll have the final temperature minus our initial temperature of 20. So this, it's okay to put this as long as these are positive quantities here. So the higher temperature over here and the higher temperature over here. And again, since we're looking at delta temperatures there, each one can be Celsius, and then our final answer will be in Celsius. So there we have it. Let's divide both sides by 500. So we have 10 times 0.03 gives us 0.3. 80 minus T equals T minus 20. Solve this. So we have 24 minus 0.3T equals T minus 20. Add 20 to both sides, so we have 24 plus 20 equals T plus 0.3T. So 1.3T equals 44. T equals 44 divided by 1.3. And that is 34 degrees Celsius. Plan. Heat equals heat. Problem number 4. A 300-gram glass thermometer, initially at 25 degrees Celsius, is put into 200 cubic centimeters of hot water at 95 degrees Celsius. Find the final temperature in degrees Celsius of the thermometer, assuming no heat flows to the surroundings. The specific heat of glass is 0.2 calories per gram per degree Celsius. Okay. Well, same sort of thing. We want the heat loss from the thermometer to equal the heat gained by the water. So let's write that. At least in magnitude. Now for the thermometer, and the mass of the thermometer times the specific heat of the thermometer, change in temperature, equals the mass of the water, specific heat of water, change in temperature. And so we have 300 grams for the thermometer. We're told that the specific heat of the thermometer was 0.2 calories per gram per degree Celsius. And our change in temperature, we're going to start with a temperature of 25 degrees Celsius, and then we're going to end up at some final temperature. So this will be that final temperature minus 25. And that'll be equal to the mass of the water, which is 200. The specific heat of water, which is 1 by definition. And then we have, it started at 95 degrees Celsius minus our final temperature. So that'll be its temperature change. So we solve this for T, we'll get our answer. And this will be 60, T minus 25 is 200, 95 minus T. Let's divide both sides by 200. So this would be 0.3 T minus 25, 95 minus T. And so it would be 0.3 T minus 7.5 equals 95 minus T. So I have let's see, 0.3T plus T equals 95 plus 7.5. T is going to equal 102.5 divided by 1.3, and that is 78.8 degrees Celsius. Problem number 5. How much heat in kilocalories is needed to convert 1 kilogram of ice at 0 degrees centigrade into steam at 100 degrees centigrade? Well, we're going to start problem number 5 with a piece of ice, and we want to change it into steam. So the first thing we have to do is we have to melt it, and that's going to take a certain amount of heat. So the heat required to melt this ice would be equal to the heat of fusion, the same amount of heat required to freeze it. and that would be its mass times the latent heat of fusion, which if it were a kilogram, 1,000 grams, and the latent heat of fusion for water is 79.6 calories per gram. So this heat is 79,600 calories required just to melt the kilogram of ice. Next thing we have to do is we have to heat it up to 100 degrees Celsius, I'm sorry. So up to steam. So this is the heat to melt. This is the heat to heat it up to 100 degrees. And that will be equal to the mass times the specific heat times the change in temperature. So that would be 1,000 times 1 times 100. And so that gives me 10 to the 5 calories for that. And then we need the heat to transform it from water at 100 degrees Celsius to steam at 100 degrees Celsius. So that will be the heat of vaporization. And that's mass times latent heat of vaporization. This one's of fusion. So that would be 1,000 grams. And that is 540 calories per gram per degree, calories per gram for the latent heat of vaporization. So this is 5.4 times 10 to the 5 calories. By far the most heat required in these three processes. So if we add all three up together, we can get the total heat required. So our total heat, well, the heat to melt it, plus the heat to heat to 100 degrees, plus the heat to make it into steam. And so that would be 79,600 plus 10 to the 5 plus 5.4 times 10 to the 5. And that gives us an answer of 719,600 calories. Or approximately 720 kilocalories. So that's our answer. Problem number 6. If 25 kilograms of ice at 0 degrees centigrade is combined with 4 kilograms of steam at 100 degrees centigrade, what will be the final equilibrium temperature of the system? Well, in this problem, we've got an extra challenge. I mean, in the calorimetry problems that we've done so far, we said heat loss equals heat gain, and we're going to do the same thing here, only we have to have enough heat to melt the ice, and we have to have enough heat loss from the steam in order to cool the steam into water. So we have two phase changes going on, and we have to account for that. So we'll say again that the heat lost should equal the heat gain. At least some magnitude. And for the steam, that means we're going to have to cool the steam, which would be the mass of the steam times the latent heat of vaporization. That's to go through the phase change from steam to water. And then we're going to have to cool it further to some final temperature. The mass of the steam in the form of water times the specific heat of water. And we're going to go from 100 down to some final temperature. And that represents all the heat that was lost by the steam. And that should be gained by the ice and then the water of the ice that's being heated up to that final temperature. And so over here, we'll have the mass of the ice times the latent heat of fusion, that's to melt the ice, plus the mass of the ice times the specific heat of water, some final temperature minus 0. So we're going to start from 0. And all that is the heat gained. Well, we know all these quantities. We know the mass of the steam. We know the latent heat of vaporization. We know the specific heat of water. And we know the latent heat of fusion and the mass of the ice. So we know all these quantities except for T. So we can put the numbers in and solve for T. So let's do that. We had 4 kilograms of steam. So this mass of steam is 4,000 grams. The latent heat of vaporization is 540. That's the mass of steam. Specific heat of water is 1. 100 minus T. And the mass of our ice was 25 kilograms. Latent heat of fusion is 79.6. So we have all of that. And if we were to multiply 4,000 times 540, we would get 2.16 times 10 to the 6 plus 4,000 times 100 would give us 4 times 10 to the 5 minus 4,000 times T equals, and over here 25,000 times 79.6 gives us 1.99 times 10 to the 6 plus 25,000 T. Put all the T's on the same side and put all the numbers on the other side. So here we have 2.16 times 10 to the 6 plus 4 times 10 to the 5 minus 1.99 times 10 to the 6 equals 25,000 plus 4,000 gives us 29,000 T. And so T will equal all of this, which is 570,000 divided by 29,000. And we get 19.7 degrees Celsius. That's our final temperature. Problem number 7. How much heat in kilocalories must be removed to make ice at minus 10 degrees Celsius from 2 kilograms of water at 20 degrees Celsius? The specific heat of ice is 0.5 calories per gram per degree Celsius. Problem number 7. How much heat in kilocalories must be removed to make ice at minus 10 degrees Celsius from 2 kilograms of water at 20 degrees Celsius? The specific heat of ice is 0.5 calories per gram per degree Celsius. Did we want to look at the problem?
Yeah.
Sorry, so you're just kidding. Okay, so we need to cool down this water from 20 degrees Celsius down to 0. We need to go through a phase change to change this water into ice, and then we need to cool the ice down to minus 10 degrees Celsius. So we need to do 2 coolings and a phase change. So the heat required will be the mass of the water times the specific heat of water times the change in temperature of the water plus the mass of the water in the phase change, the mass of the water times latent heat of fusion, and then when it's changed to ice, we'll have the mass of ice times the specific heat of ice times the change in temperature of the ice. So all these heats we have to add in order to calculate how much heat we need to remove in order to get it from 20 degrees Celsius down to ice at -10. So these numbers will be the mass of the water, which was 2 kilograms. Specific heat of water is 1. We're going to go from 20 down to 0. We have the mass of the water again. Latent heat of fusion is 79.6. The mass of the ice is the same as the mass of the water, only now it's ice. That's 2,000 grams. Times the specific heat of ice, which is 0.5. And our change in temperature there will be 10, because we're going to go from 0 down to -10. So these numbers are, this will be 4 times 10 to the 4, plus 2,000 times 79.6 gives us 1.59 times 10 to the 5, plus 2,000 times 0.5 times 10 is 1,000 times 10, or 10 to the 4. If I add these three together, I get 209,200 calories, or approximately 210 kilocalories. Problem number 8. The R value of fiberglass batting, 3.5 inches thick, is 11 feet squared, degree Fahrenheit, hours per BTU. What is the thermal conductivity in BTU per feet per degree Fahrenheit per second? On my card. All right, so we want to find the R value of fiberglass batting, or actually we want to find the thermal conductivity. We're given the R value, and in general, this is problem number 8. We would say the R value is the length, or the width of the fiberglass divided by the thermal conductivity. So we can work this out and get the thermal conductivity is the width in terms of length divided by the R value. So we're given that the length was 3.5 inches thick, and that works out, well, kind of works out. 3.5 inches thick, and the R value was 11 feet squared, Fahrenheit degrees per BTU, an hour down here. We need that in the units of BTU per feet per degree Fahrenheit per second. This is per hour. So I'm going to multiply this by 1 foot for 12 inches, and also 1 hour per 3,600 seconds. So I'll get rid of the inches here and one of these feet, and that'll give me the units required. So I have 3.5 over 11 over 12 over 3,600. And that gives me 7.36 times 10 to the minus 6 BTUs per feet per degree Fahrenheit per second. Will be the thermal conductivity. Problem number 9. A slab of concrete and an insulating board are in thermal contact with each other. The temperatures of their outer surfaces are 68 degrees Fahrenheit and 50 degrees Fahrenheit. determine the rate of heat transfer in BTUs per feet squared per hour if the R values are 1.93 and 8.7 feet squared Fahrenheit degrees hours per BTU respectively. All right, on this problem, oops. Let me find another. Now, in this problem, we're looking for the rate of heat transfer. Whenever you say rate of something, you're thinking about something per second. So if you have heat transfer per second, you've got energy per time, otherwise known as power. And if it had just been one slab, then we would have just said power equals Ka, thermal conductivity times A times the change in temperature over L, otherwise known as cattle. But we have more than one slab, so we have to deal with several slabs with different thermal conductivities. And so if we use the R values, which is generally L divided by K, then this transfers in a more general sense to this. Power equals area, change in temperature, over the summation of the R values. In other words, our R value is L over K, so we have the R values in the denominator here, we add those together. So here we're going to go from temperature difference of 68 degrees to 50 degrees Fahrenheit. And so this will translate over, say, a foot square. So 1 foot squared, 68 minus 50, or the summation of our R values, which will be 1.93 plus 8.7. And so that will be 18 divided by 10.63. Gives us 1.69 BTUs per foot squared per hour. So that is the rate of heat transfer or the power through this section. All right. Have we? Okay. Problem number 10. A cup of coffee is enclosed on all sides in an insulated cup 1/2 centimeter thick in the shape of a cube 10 centimeters on a side. The temperature of the coffee is 95 degrees Celsius and the temperature of the surroundings is 21 degrees Celsius. Find the rate of heat loss in joules per second due to the conduction if the thermal conductivity of the cup is 2 times 10 to the minus 4 calories per second per centimeter per degree Celsius. This is a good practical problem if I ever want to open up my own coffee shop. Sell coffee in a cube, enclosed cube. Maybe put a straw through one corner so that you can actually drink the coffee. But what we're going to do is enclose this coffee in a cube on all 6 sides. So we have a cube that's 1/2 centimeter thick. So the length we're talking about is 1/2 centimeter. And we're 10 centimeters on the side, so the area of one side would be 100 centimeters squared, but we have 6 sides. So we're going to enclose this coffee on top, bottom, and the 4 sides around it. So our total area is going to be 6 times 10 squared, or 600 square centimeters. So now we would say that the rate of heat transfer, which is cal, will be the thermal conductivity of the cup, which is 2 times 10 minus 4. In terms of calories per second per centimeter per degree Celsius, multiply that by our area in centimeters squared. Our change in temperature is 95 minus 21 because the coffee is 95 degrees Celsius The ambient temperature is 21 outside, so that's our difference between the two sides of the wall. And our length is 1/2 centimeter. This answer will give us calories per second. And I didn't actually figure out that number. So let me figure that out right now. And that number for calories per second is 17.76. Very patriotic number. We're going to multiply that by the number of joules per calorie. There's 4.186 joules per calorie. And so when we do that, we come up with an answer. 74.3 joules per second. So that's our rate of heat transfer from this coffee cup. A child has a temperature of 101 degrees Fahrenheit. If her total cross-sectional area is 2 square meters, find the energy lost each second in watts due to radiation, assuming the emissivity is 1. Assume the room temperature is 70 degrees Fahrenheit. Well, this problem, we're dealing with radiation, so we have Stefan's law. And Stefan's law says that everything that has a temperature is radiating energy per time. In this case, the child is radiating to the ambient area around her, but the ambient area around her is also radiating into her. So we have to take the energy that she is putting out minus the energy that the surroundings is putting into her. So we write that as the power is equal to sigma, the Stefan-Boltzmann constant, times the emissivity times the area times the temperature of the child to the 4th power minus the temperature of the area surrounding to the 4th power. So we're taking the energy she emits minus the area that's emitted into her, or the power that's emitted into her. So this is the Stefan-Boltzmann constant, which is 5.67 times 10 to the minus 8. Kind of easy to remember, 5, 6, 7, 8. Times the emissivity, which is 1, times the child's area, which was given as a cross-sectional area of 2 square meters, times the temperature of the child to the 4th power minus the temperature of the area to the 4th power. And I really should figure out what those are in terms of Kelvin. So we have to go to the absolute temperature scale in this one. So if the child has a 101 degree Fahrenheit temperature, we need to convert that into Kelvin. Let's convert it first into Celsius. So temperature Celsius is 5/9. This is the temperature of the child. And this is temperature Celsius, 5/9 the temperature of the child in Fahrenheit minus 32. 5/9 times 101 minus 32 gives us 38.3 degrees Celsius. And that would be equal to 38.3 plus 273.15 gives us 311.5 degrees Kelvin. That's the child's temperature in degrees Kelvin. The ambient temperature is 70 degrees Fahrenheit. The temperature of the area surrounding the child will be 5/9 times 70 minus 32. 5/9 times 38 gives us 21.1 degrees Celsius, or 294.3 degrees Kelvin. Just trying to give myself a little bit of room to finish this problem here. So we have the two temperatures there. That's what we're going to put into here. And so we have power is equal to 5.67 times 10 minus 8 times 2. Times 311.5 to the fourth power minus 294.3 to the fourth power. If you calculate all that out, you get 217.4 watts. So that's our answer. Problem number 12. A super insulated house is at a temperature of 20 degrees Celsius. The temperature outside is 0 degrees Celsius. The surface area of the house is 200 square meters and the emissivity is 1. Approximately how much energy is radiated in watts per second? Alright, let's approach this like the last problem. We have a super insulated house at a temperature of 20 degrees Celsius. We need to convert that temperature into Kelvin, and the same thing with the outside ambient temperature of 0 degrees Celsius. So on this, problem number 12, we would use the same formula. Stefan-Boltzmann constant, emissivity area, times the temperature inside the house minus the temperature outside the house, both to the fourth power. And if we put in our values for this problem, this would be the Stefan-Boltzmann constant, 5.67 times 10 minus 8. We're assuming the emissivity of the house is 1, and we're told that the area of the house is 200 square meters. The inside temperature is 20 degrees Celsius. So let's take a little side note here, which would be equal to 293.15 Kelvin. And the outside temperature is 0 degrees Celsius, freezing, and that is, of course, 273.15 Kelvin. So we're going to put that up here, 293.15 to the fourth power minus 273.15 to the fourth power. That gives me an answer of 20,587 watts. So that's how much energy in joules per second that we will lose from this house. Problem number 13. A 5-gram coin is dropped from a 300-meter building. If it reaches a terminal velocity of 45 meters per second, and the rest of the energy is converted to heating the coin, what is the change in temperature in degrees Celsius of the coin? The specific heat of copper is 387 joules per kilogram per degree Celsius.